Okay, in this video, I just want to discuss a few things that don't have to do with calculating the volumes, but have to do with understanding why we are doing this. So I get asked quite often by students, why are we learning to calculate volumes of rotations? And I think there are a couple of reasons. So let me begin with the first one. So let's ignore volumes for the time being. Let's go back to the idea of just an integral as an area under the curve. So here's a graph of a function. And let's say I'm interested in calculating the area under the graph of the function from a to b. And let's just say that the function is very complicated. So I'm going to write down something that is kind of going to look funny, but it'll make sense in a minute. So I have a complicated problem. And I don't know how to solve this. I don't know how to actually calculate that area. So what I'm going to do, in fact, this is what we do in calculus. So what I'm going to do is I'm going to approximate this. I'm going to say, okay, let me not solve this exactly, but let me chop this region into two regions. And the way I'm going to chop it up is by constructing two rectangles. So I'm going to take the midpoint, look at where the function passes over it, take that rectangle, calculate the areas of those two rectangles as an approximation to the area I want. Okay, and then we can go ahead and say, okay, maybe I can do even better. I can split this into four rectangles, and now I can take that strip, that strip, that strip, that strip, and get an even better approximation. And we can keep doing this. We can chop this into finer and finer rectangles. So what we're really doing is we're taking the complicated problem and we are approximating it by a simpler problem. And the simpler problem usually has some finite pieces to it. And let's say that we have n number of pieces here. And if we're really smart, we can construct this approximation in such a way that we can keep making this n bigger and bigger. So n here is just the number of strips. So as I make my strips finer and finer, I get more strips. So I can make my n become bigger and bigger. And now here's the key step. If I do everything right, then as I let my n go to infinity, as I take ever finer approximations to the area under the curve, this approximation that I'm calculating, this number I calculate, which is the area of the strips, will actually converge in the limit to the number I really want. And in fact, it's not just that it will converge in the limit to the number I want, but that limit actually is the definition of the area between A and B. So this is, you can either say this is the definition of what I want, or it's a way of calculating exactly what I want. This process, where we begin with a complicated problem, we approximate it, and we let the approximation become exact in the limit, is actually a really key and important idea. In fact, in reality, in real life, there are very few quantities in science and in engineering that we can calculate exactly without doing this process. So in the absence of this idea, most of physics, most of engineering, and the quantitative part of chemistry would probably be impossible. This is the one trick we have to calculate complicated things. And it's this idea. It's the fact that you can take a limit, and if that limit exists, what you actually have is the exact answer to your problem. This is the key thing that makes all of quantitative calculus, all of quantitative analysis works in science. And of course, this is exactly what calculus is. And that's why it's important to understand calculus. It's important to understand what this technique is. Okay, so what does this have to do with volumes? Well, what it has to do with volumes is that the volumes of rotations, calculating the volumes of rotations, illustrates this idea starting from really simple case where you are just doing an area under the curve to more complicated cases. So take the idea of using disks, for example. So here's a volume that you want to calculate. So that's our complicated problem. We can't calculate it. So what we do is we approximate it with disks. Right, so we have a series of disks that approximate this volume, much the same way that the strips approximate the area. And now we take the limit as the number of disks become infinity, or as the thickness of disks becomes 0. So it's exactly the same idea, except what we've done is we've gone from something that was a simple strip now to something that's a little bit more complicated in the approximation, and that complicated thing is a disk. Okay. The washer method is again an example of exactly the same thing. So if you're looking at calculating this volume, then we approximate the volume with a washer, and basically just like the strips, we now stack up the washers on top of each other. We take the limit as the thickness of the washer becomes 0, so essentially n is the number of washers is going to infinity, and again now we're able to calculate something that originally we could not calculate. And the relation of this to this is exactly, in some sense, the relation of this to this. That is, we've just made the thing that we are approximating with a little bit more complicated than the previous stage. And then finally, of course, the method of cylinders. Now approximates this with a cylindrical shell. And so that's again a little bit more complicated than a washer. So that's the first reason why we study calculating volumes of rotation. It's a very simple illustration of this idea. The idea that you can take what looks like an intractable problem, approximate it with a simpler problem, and then take the limit to get the answer of the original problem. There's a second reason why volumes of rotation are interesting. So if you think about it, what you've learned in 115 so far is basically single variable calculus. So given a function f of a single variable, you can do things like calculate the integral of f of x. And according to this interpretation, basically that should allow you to calculate areas in 2 dimensions in the xy plane. Now what's cool about this volume of rotation business is that we are using a technique that works only in 2 dimensions to do something in 3 dimensions without actually making our calculus more complicated. In other words, we really should be using a multivariate calculus integral to calculate this volume. But what we're doing is we're exploiting the symmetry in here so that we can take the radius of the disk and relate it to something that's just in the xy plane. And it's that symmetry that allows us to take a single variable calculus trick and calculate a higher dimensional volume with it. So this idea that you can use a simpler technique which is developed in low dimension to do something in high dimensions, if the high dimensional object or the high dimensional problem has some symmetry in it, that's a really useful idea. This is used very often in physics and engineering, where the high dimensional problem at first glance just seems intractable because you don't have the technical tools to calculate it. But if it's symmetric, very often you can use a low dimensional tool to solve that problem. And this may be the first time where you've seen an application of this idea. Okay, one last point I want to make. And that is, all of this is fine. From this abstract point of view, this looks really interesting. But when you actually do the problems, there is all this tedious business of setting up the formulae and solving it. And there's a point to that too. And the point is that things that we develop as an abstract technique actually require some practice, require some cleverness to be translated into solving a practical problem. And a lot of what you're doing is understanding how to take something that is developed as an abstract idea and apply it to a real problem. And very often in more advanced problems, even applying an abstract idea to a concrete problem can be a fairly complex research issue. So this stuff about figuring out what the radius is in terms of the area that you're rotating is actually a complicated process, and that's why sometimes you have to struggle with it a little bit. Okay, I hope that helped to give you some idea about why you're doing this.